becomes...
It shifts, like sine is cosine and cosine is sine.
Yeah,
Like,
which to use in general. And I have a technique for that.
Okay.
You know the graph of sine looks like that.
Parabola.
And the graph of the cosine is in fact just the exact same thing, but shifted forward. It's not a parabola. Sine is a thing that starts from 0, it rises and falls and rises back, and then it just repeats like that over and over again.
Okay.
It's really one of the most fundamental kind of forms of cycle that a lot of things are modeled on. Cosine, in fact, is the same thing, but you start here.
Okay.
Notice it's the same pattern. It just starts at the top, it falls, and then it rises back up again.
Oh, okay.
So there's not really any other difference. But the key important concept key concept there. I missed part of it. Is there's a starting point for each of them. Sine starts at 0, cosine starts at 1. So this fundamental thing that I never forget is that the sine... Alright, well, it's not going to beep at me anymore, because I took that away. You're not allowed to beep anymore. You work for me.
Almost. Maybe in the back. Looks like a moose.
You work for me. For this.
Whatever. That's okay. Technical difficulties bound to
It's that
happen.
cord.
My mom's Roomba chewed up my iPhone cord. And now it won't work and I'm irritated.
There we go. Alright. More issues. Let me make sure the recording is still live.
Oh, there we go.
The reason I
John
have that
King,
is
hey.
that all this stuff connected.
They're coming for me.
Oh, but that one would be perfect.
So we do it.
We had another guy come in today. He said 350.
Okay, I think that's
Okay.
fair. Yeah.
Okay.
Alright.
So the key thing to remember is that the sine of 0, therefore, is 0 because of that starting point.
Is this how
And the-
some people can just like you know, like in the circle there's I know that there's units attached to things and you just like can memorize them or you can is this how you would know?
Yeah,
Okay.
this is how I know for sure which one makes sense and which
Okay.
one doesn't make sense. So, one of the things that comes up a lot in this particular class is, say I have a block that's sliding down, and I'm trying to remember. Still gonna do it. I'm trying to remember which is mg sine of theta and which is mg cosine of theta. So, well, if I just say I guess at random, I put sine in here, and therefore cosine in here, because I can't quite remember. I'm under pressure. Is sine going to be right? Well, imagine the case where the ramp gets flatter and flatter and flatter.
So like
which-
this comes down.
Yeah, it comes down, which ultimately would lead to a block just sitting flat. Now, does it have any force pushing it forward? It doesn't. So that's the one that should go to 0. And
So
the
then
sine
0
we
is
can see
sine.
approaches 0, so sine is the right one to go to.
So this curve is working in which direction, left or to the right? I'm not understanding this. You're saying this
well,
is
the
going to
theta,
0, but-
yeah. So this is theta along here,
Okay.
and the theta is just kind of dropping to 0.
Okay.
I
To
see
make
what
it
you're
even.
saying. So it goes okay.
Yeah. One more try here. Just turn sound. So that's and the same technique will work in lots of different cases where you can't, it has to be one of them. It's a vector you need to break down, and you can't decide which makes more sense. So you ask yourself, what would happen if that angle were to collapse to 0? Which of the two would give the right result in that particular case that breaks the 50-50 tie?
Okay.
And it lets you pick the right one. Because you can go through all the geometry and just make one little mistake in the middle of there and get it backwards. Because it doesn't have any meaning for you. So this allows it to have some meaning.
To get to the 0.
Which one goes to 0 in the right way? If you have a more specific question of one that you were struggling with deciding which was which.
We also wanted to know, we've noticed that the energy problems that we went over, they give you theta, but we never use it. Is that just because it's this problem, or is this a trend?
It's a bit of a trick. The reason that works is, well, it's not always going to work, of course.
Okay.
If they've given you the height, and you're thinking about energy, and you're thinking about gravitational potential energy,
MGH.
then it's about MGH. And the theta here doesn't matter unless they've given you the distance. If they've only given you the distance and not the height, then you have to get the height.
From the, okay.
Because it is, again, either d cosine of theta or d sine of theta. Ask yourself, which one goes to 0 in the right way?
So,
It's sine, yeah, because the height should go to 0.
okay. So it's just, it happens with these problems we didn't really do anything with
So
it.
it's only when we're trying to find the height that we would use in this particular.
Yeah. Yeah, if
Because
they
we're
gave you
just
the distance,
trying to-
and sometimes they'll do that,
Okay.
that could also be relevant if we're talking about work, if there was friction. So if we had a mu, then there could be a force along this distance, which might be mu times the normal. So the work would be mu times the normal times the distance, in which case the distance really matters.
So that's
And you
when we
wouldn't
would use
ignore it.
cosine. Or still sine.
You'd use cosine probably to get the normal, but again, you just ask
Okay.
yourself, the normal is either going to be mg sine of theta or mg cosine of theta. When we go to the flat case, the normal, well, it's just holding the full weight up. So when we go to the 0 case, it should be 1. And cosine is the one that goes to 1, so therefore it must be cosine. I was doing that for years, looking at other students' work, and I would immediately know that their thing was wrong. And then I would do it the way they do it in class, and they take you through all the geometry, and then it's like, this angle's down here, and all that. And then they would be wrong half of the time. So finally I said, this is how I know. So now I just kind of show that to you up front.
So
Oh,
what
thank
about
you.
what about if the triangle is tilted?
Well, it can get more
Because
complicated.
that's when he switches it, and then.
I don't understand that guy.
For 125, I mean, they tend to stick with this triangle or this triangle.
He doesn't.
Oh.
He does all, yeah.
He swaps it, he angles it, and so then
he
we
wants
know
you to
that.
know it, but we, yeah.
Yeah, so we know that then y doesn't become sine, x becomes sine.
Yeah.
But you're always trying to lower this ramp essentially to 0, is what you're
Yeah,
trying to
I'm
say.
watching what happens as I squish it down until I get
Okay.
the right outcome. It's really the sine and cosine are like divvying up a piece of the vector, who gets what amount, and the right piece has to get the right amount as you make the vector go 100% in one orientation.
Ish.
You kind of have to apply it a few times to get the idea, but
Okay, so that was the main question that we had done after we did 6. And then, should we just go over the formulas and the units for what you would like? And then we can ask about specifics, or what did you have?
I feel we had another question on here.
I wrote number 6, but we can do
Yeah.
that in a bit. I kind of had got half of it. Yeah, I have it somewhere here. Oh, yeah, okay.
Yeah, I just pretty much have formulas. units.
Go over the units then? Is that what you would like?
Sure.
Okay. So we know that force is a new. When do we know it's like joules versus watts? Power is watts.
Yeah.
And then everything else essentially for energy would be a joule.
Yeah, most of the energy you're going to see is all joules.
Okay.
Power
What about the
is
Newton meters and the
energy
Newton-
over time, so
Okay.
that's why watts is really joules per second. It's
Okay.
watts.
Okay.
Usually with the power questions, it's about finding the source of time. And it might be assuming it's a second. Somehow just working everything out to stick with
Okay.
the time being a second. That's otherwise really obvious.
What else did you have?
Oh, I don't know. I thought we were gonna go over all of them, like all formulas that we would need, all units.
It's my pen that's low on power.
We can trade?
No.
Oh no, actually it won't work because it's
I have batteries. That's
Okay.
why it's negative.
So formulas and units basically.
Yeah, okay.
And we have some of them, but it would just
Yeah,
be
you
good to
should.
walk
I
through.
want to have them organized.
Right. So 6 is energy, 7 is impulse and momentum, 8 is rotational kinematics. Oh, I had a
Okay.
question for you about 8. Just a side note. For the kinematics, just linear basics, you know, you have your formulas, and then I was reading something that says like, okay, let's say we're looking for acceleration. Despite the fact that we're looking for acceleration is a given, like it's a known variable that you are looking
It's
for.
a known constant.
Right.
It has to be.
So then you would look for the actual one that's missing to figure out which equation to use. Would that same principle apply to rotational as well? Because it's the same.
Yeah.
Okay,
Except
so you
that
can.
it's alpha.
Omegas and
But,
stuff like that.
yeah.
But you can just do the same thing. So if you're not certain, you could go to linear and then.
Yeah.
Pop
So
over.
if you want to go through all the
Yeah, let's
formulas
do it
from the
all.
start,
Yep.
the most basic thing is velocity, right?
Mm-hmm.
V naught plus AT.
Mm-hmm.
That's the basic kinematic. You integrate that with calculus. That's
Right.
where you get the delta x1. V naught t plus 1 f at squared,
Okay.
which quite often turns into free fall, which is typically delta y equals v naught t minus 1 half gt squared.
Okay.
And then v squared equals v naught squared plus 2a delta x.
Mm-hmm.
So those are all your basic kinematics. Then you have all the parallels in rotational.
Right. It's like omega equals.
Omega naught plus alpha t.
Does it look like we're missing one, or is it just like you put it on this side? Doesn't he make us usually have like 4 or 5? Not that we use all of them, but
I
yeah,
have that somewhere.
in the very beginning.
There's sort of 3 basic ones.
I'm just yeah.
Delta theta equals omega naught t alpha t squared.
How many is that? 1, 2, 3. Match them. 1/2. 2x. 18. Okay.
So there's the 2 different versions of kinematics. Almost all the questions you're asked have constant acceleration
Okay.
in some fashion. So it's a question of whether or not you can make use of it. Let's see. So from there, we would go to the F equals ma type stuff. Obviously, that's good to have, but also the acceleration for the system equals the sum of the force over the sum of the mass. And that applies when we have a chain of some sort.
Can you review the system and like there's the external system and then like the internal system?
Yeah, so this is, here I'm saying that I kind of draw a box around these two that I believe are going to accelerate together. And so I don't care about the tension because their acceleration is the same for the
Okay.
two of them. So the sum of the masses is the two masses. The sum of the forces is the backwards force that exits the system
Okay.
and the forwards
Forward.
force that exits the system, which is gravity reaching out and affecting that system. 'Cause
And
gravity is from the outside, it's the Earth.
So, would this be internal or external, or does this have nothing to do with that?
It's the forces that are external.
Forces are external.
That's why the tension doesn't matter.
Okay. Forces are external.
Like you have the chair pushing on you, you have gravity pulling on
Mhm.
you, you have air pushing on you. You also have all sorts of cohesive forces that are keeping you together. Van der Waals and all the different chemical, molecular bonding forces. But we can ignore all of those. So in fact, it's impossible to analyze just about anything without looking at it as a system. It has to be a
Okay.
single electron. Which isn't really the domain of this class. So that's useful when we want to look at a lot of them. So that case, or if I have, for example, 1, 2, 3 blocks and an outside force pulling, I can look at it as a system.
Because it's
Say I was given the outside force, I can get the acceleration for the whole system, and then I can get the individual ones once I have the acceleration by drawing a circle around some part and realizing that now this is exiting that
okay.
because it's a different system. So you can draw the system any way you want as long as you can draw a circle around it. Maybe
Okay.
a sphere around it.
So it's a unit.
Surface.
Okay, so then from here you're saying, so we have F equals ma, now we're saying that this is the acceleration, and then from here, where would we?
Let's see. The next place the class goes is energy,
Okay.
right? So your forces or forms of energy are kinetic, 1/2 mv squared, and you have gravitational,
Okay.
GH, and you have spring, kinetic, potential of a spring, 1/2 k delta x squared. Normally written as x squared, but I'd write that to emphasize that it's the change in x that really matters. So energy can trade off between those, and the starting point for most questions is the energy initial equals energy final.
Mm-hmm.
That's within the system, but the system, when we look at it at this point, includes gravity. So that's a different perspective than here, because now we're allowing gravity and the Earth to be part of the system with a much
So it's
bigger
a bigger-
circle,
Okay.
including the entire Earth.
See what you're saying.
There can, however, be work in there, which typically is friction.
Mm-hmm.
From this point up here, we kind of left off. The force of friction is mu normal,
Okay.
which is often
Mg.
mu mg, or could be mu mg cosine of theta, are the most typical, but it depends on where the theta is, and you need to use that test to determine how much friction should there be given the angle. Right? If something's falling down the side of a wall, there's no friction at all. If it's sliding along a flat surface, it should get 100% of the friction.
Mm-hmm.
So that's the 1 or the 0.
Okay.
So given that we have that, therefore work can also be a form of energy, which then could be mu normal.
So we're substituting FD is now mu normal because of the friction. That was actually, I think that was like problem number 3.
That can be one of the trickiest things. So
Yeah.
if something slides down a ramp again,
Okay.
it's always blocks on ramps, I guess, and it has a mu in there and a theta
Mm-hmm.
and a mass,
Mm-hmm.
then the energy initial is the energy final. The energy initial is going to be all mgh, because
And it's sliding down
at a
at the
height.
top,
Yeah,
right?
so
And then
that's
at
what
the
it
bottom,
starts
it's
with.
kinetic.
At the bottom, it's got kinetic.
Yeah.
But it's also lost energy to work. And I account for that, this is the counterintuitive part, by putting the UN on the right side.
Oh, because we have to, because of the work. Okay.
Yeah, so it has to be accounted for on both sides. It's like an accounting balance sheet. The money has to go somewhere.
Right,
It can't go
'cause
nowhere.
Another
The energy has to go somewhere. So this is all there was, and now it's there, which means it went into heat or noise or whatever. Right, it's both. It's vibration and heat and sound, damage, and whatnot. Okay. So that's the basic thing on energy. And then after energy, you get into momentum, or maybe
Impulse
before,
momentum, yeah.
depending on how you want to look at it. Momentum is mass times velocity.
Mm-hmm.
Impulse is force times time. Impulse is change in momentum. And therefore, when we put all those together, force times time is mass times change in velocity. And that ends up being the equation that you tend to apply
Yeah.
over and over again. But you can also have that momentum initial equals momentum final, which
Okay.
you can sometimes pair with energy initial equals energy final. That often produces problems that are difficult to solve because they become quadratic. And that's why we have that formula that we went over, which is which splits us into the two cases where we have elastic and inelastic. Oh, testing my spelling here. Inelastic. Elastic is a bounce.
Is a what, sir?
It's a bounce.
Yeah, okay.
It's typically a baseball bat, a rubber ball, pool, tennis, pretty much basketball, pretty much games with balls. It's mostly an elastic bounce.
Okay.
Inelastic is often collision, crash, stick,
Okay.
stick together, clay, things involving bullets, because they don't meet nicely usually.
Okay.
Inelastic means that the V final is together. So they're the same. They stick together, they have the same final
Okay.
velocity. Elastic means the V final is different.
Okay.
Elastic, however, so inelastic becomes easier because there's only the one variable to solve for in the end. Elastic causes those quadratics to be developed. Of course, if it's a written test, you could get a lot of the points just for writing the equations out, not actually solving them. However, we have that shortcut that we looked at, which was specifically for elastic, where we said that V center of mass is the sum of mv over the sum of m in a given dimension.
Okay.
And then V final for a particular particle K, is equal to
The center of mass, I think it was.
V center of mass minus 2V initial K.
Oh, the other way. 2V center of mass minus.
Other way around. You see, I forgot it again since the last time we talked about it. It's because it doesn't mean anything to me. The part about this that means something to you is the part that's going to stick.
Well, let's hope
If you get to
so.
the point where it means something.
It means something to Stephanie right now.
And this tends to be the key to doing elastic, is realizing that they're stuck together, so it's not two different variables. It's just one V final for everybody.
That was another question. So.
Another key to these is to split X and Y into separate questions, because these rules are true in both dimensions separately. That
Okay.
produces two equations, which tends to be a system that you can then solve. Hopefully a linear system. If you've either used this trick, otherwise you should get a linear system most of the time.
Okay.
If you didn't get a linear system, it's probably because you didn't use this equation. That one, because that solves a quadratic for you, basically. If you're real slick, you can avoid ever having to do that.
One day. One day.
Well, you just end up doing something worse.
Oh. Okay.
It's somehow become my whole thing. You can deal with the easy part. Whatever is the worst possible problem, I'll deal with that. Alright, so after momentum, collisions, energy, then you get into rotating systems,
Yes. Your favorite.
which tends to be all about just that one thing, which is acceleration equals v squared over r.
And then the radians and the degrees. That's something that is confusing.
The radians is just a unit, right? It's not
Yeah.
an actual.
It's like 2 pi something, and then it's like 360 divided by 2 pi is something. Something that clearly I don't know. Oh, baby ones.
No,
Oh.
baby, don't do me that way. What are you doing? Yeah. So back. So what about acceleration? People are gonna get hung up.
Center mass is chapter 9, right?
Yes.
I mean, there was one center mass question here, but it wasn't really anything like, yeah. Oh,
Gotcha.
nice drop off.
Okay, so then spinning things. So it all starts with acceleration is v squared over r. We also sometimes need s equals r theta.
Okay, and
Or-
S is a distance, right?
S is a distance,
Okay.
yeah. It's really an arc length.
Oh, right. For the, okay, that's right, okay.
And then which leads to, by taking a derivative, v equals r omega, because v is the derivative of distance, and omega is the derivative of theta,
Okay.
because omega is always going to be radians per second,
Mm-hmm.
and we have to watch out for RPMs, which is actually revolutions per minute.
So in this case, we would change the minute to seconds.
Yeah, so we need that conversion factor.
Your favorite 300.
So if I needed to go from RPM to radians per second,
Uh-huh.
I would say it's more radians, so it would multiply by 2 pi,
Okay.
and then there's 60 seconds per minute, but it's actually less because we're going to seconds, so I would divide by 60, and so therefore it's actually going to be pi over 30.
Okay.
And then the next derivative of that is alpha equals r, or wait a minute, A, this is distance. It's a linear distance on the left side.
Okay.
Equals R alpha.
And alpha's always in radians.
Yeah, alpha is going to be radians per second squared,
Oh.
just like acceleration is per second squared. Only
Okay.
this perspective over here is angles or radians. This perspective over here is distance or meters,
Okay.
or meters per second or meters per second squared. The acceleration is always inward. I haven't seen in the questions that you had that you had an alpha or an angle that you had to work out, but the acceleration is to the center
Right.
if, this is true, if alpha is a constant. However, if, no, there's the center,
Mm-hmm.
and it would point ahead of the center, leading, if omega is positive and alpha is positive.
What about tangential in relation to this?
Yeah, so
stuff?
this one here has a tangential equals 0
Okay.
because alpha, or actually, no, alpha is a constant, alpha is 0. This is alpha that's positive, and here we have a tangential, which is equal to R alpha, because alpha is positive, the whole thing is positive. This is the thing that's speeding up. And then this perspective here, if I have the actual acceleration vector, that's what this is, here's the A vector, pointing back from the center, that's a case where omega would be positive and alpha would be negative.
What do you mean pointing back from the center?
Well, so the thing is just going around in a circle,
Right.
constant speed,
Mhm.
spin something around your head. The acceleration is always pointing right back towards you.
Okay.
If you think about it, if you've ever spun something around
Right,
your
it
head,
right.
notice the lasso thing, my hand does not hold still. And the reason my hand doesn't hold still is because it has to continuously lead the actual center. So it's actually,
Okay.
I'm intentionally, the thing I'm spinning is back there, and I'm intentionally leading with my hand a little bit.
Okay.
And that's what causes it to speed up. And then once you get it to where it's steady, because it won't stay that way because of friction, but briefly you can just hold it there above your head and it would just go around in circles. But the reason you're holding it directly above your head is because you have alpha constant, or alpha 0 at that point, and it's just going around in circles. But
Okay.
there's always tangential acceleration to keep it on the centripetal path.
Right.
But because here there's a force being applied, but it is perpendicular to the direction you're going, there's no work being done, so it's not being sped up. Here, it's not entirely perpendicular. There's a portion that is in the direction you're going, and that's why it's being sped up. Or here, the same thing, but it's being slowed down.
Okay.
And you can use the sine and cosine if you have to break that down. You can use that same process of which one makes sense. If you got this here, the sine makes sense, this cosine makes sense when you let the angles go to 0.
Okay.
I have not really seen in your class these two cases. At least your instance of this class. It's always different.
Wait till it comes.
So, what other equations? Beyond that, there's just kind of...
In some
Canned
instances,
solutions
we're
to
saying
things.
that F equals MA, and the other one we're saying that F equals MG. Is one horizontal and the other one vertical?
MG is
something
just
that
a
we-
specific
yeah,
case of vertical. That's free fall.
Right. Okay. So that's
So that's
what it
that's
was.
why I wrote that down here. That's the free fall case.
Oh, yeah.
Acceleration
is-
is just negative g. So it comes up so often you think it's a rule, but it's actually just you're just looking at things vertical and there's
Right.
gravity
So
there.
that's exactly what it is. Horizontal. Cool. What shall we go over? I definitely have questions.
A typical.
Yeah.
I don't know quite what test you're looking at. You have a practice test, or was that?
No, this is the
It's
work.
just those-
This is the stuff
yeah,
we
it's
did.
just
He
those
didn't give a
chapters,
practice
huh?
test at all.
Yeah.
It's just on these 3 chapters. So what he normally
Often
does.
there is one in the book that they don't mention. If you look, there's a chapter review, which is
Okay.
really a test,
Okay.
and that's the same technique being used to write that he's going to use to write the test.
Okay.
So
So we should.
if you have to go after those.
Yeah, we're
chapter
using
reviews-
Wiley, so it's like.
Yeah, it'll be in there.
Okay. What was I gonna ask?
It's usually a little shorter.
Oh,
And
conceptually, what do we need to know from each of these 3 things? So what he normally does is he has about 10 problems total. He usually splits half up into conceptuals, half up into solving. But last time he gave us more problems, less conceptual. So last time he gave us 3 conceptual, 7 problems. And I'm thinking that this time he might do the same because we have 3 chapters that we went through that he'll definitely ask a conceptual question or just what's an example of things he asks? I didn't bring any of the stuff. Last time he asked
think
us. Oh, you have it?
I might have a test if you want to see my embarrassing test result.
I don't
Maybe we can go over that on one of our other days. That's why we're like, we'll just keep coming.
I think I have it somewhere.
I'm not here to be judgy, so I don't really look at the score.
Oh, it's unpleasant, but that's why we're here. We're working on it.
I got a 0 once on a physics test. That was my worst ever performance.
You know, I think that's just wrong. Like, showing up, putting your name on it, filling stuff out. Like,
It was a shock that I was even there. I hadn't been attending the class.
Should be like the first thing.
yeah, so this is what he usually does, and then straight.
At UCSD, like a 40% was an A. That was a good
Which college
good
did you go
showing.
to?
mirror, but
Oh,
the
okay.
physics is all the same. Whatever it's called, sure. Short description of Newton's 3 laws.
Yeah, so it would be a short description of the stuff.
Huh. Yeah, what would I ask you to describe?
I'm thinking he's going to ask
Oh,
about impulse
energy.
momentum
What's
together.
why does energy matter?
No, he won't ask that. That's just
Describe it. What is the conservation of energy, or what is the law of the conservation of
Okay, well,
energy?
that's
What is the
just-
law of the conservation of momentum?
Nothing
When is
is
energy
created or
conserved?
destroyed.
When is momentum conserved?
Okay. And then formulas.
2 answers to that. Technically, energy is always conserved, but for a given system, it's not, because energy can exit the system.
But then it just goes right back. It's like the kinetic potential thing, right?
Yeah.
Like it kind of.
It can go back and forth, but it goes into work or friction or something like that. It's just gone, because friction. What friction does is like sanding something. It damages or destroys
Oh, right,
or
so-
changes the nature of something, and then the work can go into that, which also would produce heat and sound and whatnot. Momentum, on the other hand, for any system is always conserved.
Okay.
That can be confusing because really the energy, I mean, when you add it all up, the energy is all still there. But there's places it goes that you haven't studied, so in their chemistry, basically.
This is why I know. Okay. So that was for energy. That was for 6.
Impulse and momentum is 7.
I'm thinking he's definitely gonna ask about impulse momentum theory because it like somehow relates to Newton's. I know this, and I was like trying to play
Yeah,
with it.
impulse,
I feel like he's gonna be like, how does this all go back to Newton's?
because that's a poorly understood area typically.
I'm 100% I'll ask.
Why is it that I could, if I push on something for a certain amount of time, do I necessarily cause it an impulse? What if it doesn't move?
Force times time. If it doesn't move, then you have no force.
Well, if it doesn't move, you have a balancing force. Right, so if I
So
hit
it's
something
like
with a
heavy enough.
hose, it'll probably move. But if you hit a window with a hose, it'll kind of bow out a little bit, but it won't actually go anywhere. But the impulse is still being applied, so where did it go?
Into the force and the time. I don't know. I'm looking at this formula. I'm like, where does it go? I don't know.
It goes, if this is my window here,
Okay.
and I'm over here, and I aim this hose, and the water bounces off of there and splashes in the various directions.
Okay.
Well, there are two assumptions I could make. First of all, it could hit and stick, in which case,
Okay.
remember that was the question of
Elastic and
specifically
on
it was, but
sticks.
the change in momentum for it was just it going from V to 0. It could also hit and bounce. If it bounces right off, then the change in momentum is twice the delta V.
This was this question, I think, right? This was your 2 times.
Yeah, it was doubled because it was bouncing back.
So you're saying
But if it's
forward
a
is
continuous
1.
flow, there was another one that was wind, I think. It was wind pressure
Yeah,
on
the first one.
surface. Another way to ask that, though, is the window. But so there is a force being applied,
Okay.
and it's happening over a time, but yet the window doesn't move, but that's because the window is fixed to the ground and I'm fixed to the ground. And so the impulse is literally being applied back against me. So I could feel the hose pushing back on me. I'm pushing on the ground. The window's pushing on the ground in the opposite direction. The ground doesn't go anywhere because I'm pushing this way on the ground. The window's pushing that way on the ground. And
Why are
so-
you guys pushing in opposite directions and not straight down? I don't fully understand.
Well, I'm also pushing down,
Okay.
and there's a normal
Okay.
pushing up, but those are in balance, so
Okay,
you're not
so
going anywhere in that
okay.
dimension. But then I have friction here
Okay.
that's tying me to the ground, and it has some form of friction as well, or some bond,
Okay.
which is sticking it to the ground. So it doesn't go anywhere, but there's a tension effectively across here because we're both attached to the earth, and so it's pushing the one way and I'm pushing the other way, and that's why it doesn't move, even though there's an impulse. So there's a balancing force. On the other hand, I take and if I have something here that has a mu on it, but a mu kinetic, not enough to make it stick, and then I aim a hose at it, then it's going to move. Assuming that the force exceeds the mu static. Speaking of which, another form that comes up a lot is I have that and I apply a force at an angle. There's some angle theta. There's a mu on there and there's a mass. And I want to know what's the acceleration.
Oh, he did ask this question.
That's a real common one. Appropriate for this section. It is. A common question might be, well, here you would just ask for the acceleration. The other form of it is how far does it go when you stop pushing.
He's also asked that.
If you just ask it this way, then there's a force down on it, which adds to the normal force. The normal force up is not just mg. It has an additional component, which is going to be f, either sine theta or cosine theta, which you think it is based on my technique.
Sine?
Yeah, because it should go to 0 as theta goes to 0, because then I'm just pushing the block forward. You can also pull the block this way with tension, which is like pulling a bag at the airport or whatever. Because when you pull the bag, you tend to pull up, and you actually make it lighter, and you have less friction. In which case, it would be the opposite. The normal would be mg minus t sine theta. Because you've lightened the bag a little bit. So this is the bag. This is pushing downish. Down and forward. In either case, therefore, the total force in the first case is going to be F, and then either sine theta or cosine theta, but it's typically the opposite, so almost without thinking I can just go with cosine theta. But if I was pushing straight forward, all the force should be accelerating it. And it's being slowed down by friction, mu times the normal, and the total normal there I already worked out is mg, enough to hold it up, plus f sine theta, the added normal due to the fact that I'm pushing downwards on it. And that then all equals MA. In the other case, you just get the other thing in there. If I do all that and I get myself up to a velocity, I might want to know how far does it go? The initial. How far? Well, I can do that with energy, because energy initial is energy final.
Mm-hmm.
And so the energy initial is just the kinetic. Which if we like, we could build it up and write KE. KE initial, but in the end it stops, so there's no KE. And where does it all go? It all goes into work, because the friction is going to slow it down. So KE equals work in that case. And therefore 1/2 mv squared equals mu times the force, or, well, the total force, which is just mu mg plus f sine theta. That's the force times the distance, and you can get the distance out of it. And then if we make it one step more complicated, I think this was one of your homework questions, and I want a block, and I want to let it rise up a ramp, and I want to know the distance of the ramp, then the energy initial is still just 1/2 mv squared. But in the end, it's going to have no kinetic, it's going to have done work.
And have potential.
Yeah.
Right.
We don't have this force on it, but we do have an altered normal. The normal is reduced due to it being at an angle. So the normal is mu, and then it's mg, and then again I have to decide, is it cosine theta or sine theta? They like to sometimes throw the theta in there. That don't really mess with you. One option is just refuse that and just figure out the theta here and work with that, because it's more consistent for you. Or you can just figure it out using my rule that the answers will be opposite, but it'll still work as it collapses. That probably will confuse you. So better off to just, and the reason I always show it that way is because that's polar coordinates.
Right.
Theta and r. So mu mg, and then it's a fraction of it. It's a fraction that you get to be more as theta goes to 0, so therefore it's cosine of theta. So that would be the work, mg cosine of theta. But then it also rises, but it rises a height, and we were given d instead. So I need an mgh, but the height is going to be d, and then either sine theta or cosine theta. We have to decide again, which makes more sense.
So that one would be sine.
Yeah. I've got it. And they'll just switch it up, whether they give you d or they give you h or they give you theta, or if they really want to be cruel, of course they'll ask for theta or something like that. They'll give you the h and ask for the theta. I don't see that in this class.
Okay, I think my other thing is I don't actually really know what mu is.
U is a fraction. So a lot of things, you get a fraction of it. You get to keep a fraction of your income, like 85% maybe, or somewhere around there. So friction, the friction itself is really being driven by the normal force. If I'm not touching something, clearly it's not going to keep me from moving. The more I touch it, the more I push on it, the more it's going to keep me from moving. So if I push down really hard, if the thing is extremely rough, like very rough sandpaper, the amount of horizontal force could be as much as the vertical force. For the horizontal force potentially to be more than the normal force, it has to be glue, which is a chemical bond, not just a physical structural bond. So friction really is not thought of as being something that has a glue factor to it, although in real life, all things do, we have static bonds that break and occur and break all the time. So mu is typically 1 or less. So it's a fraction of how much of the normal becomes horizontal. These are perpendicular forces, right? So the two have to be perpendicular, one way or the other, to get a mu. Even if, say, I want to think about something falling down a wall, well, there's no friction unless I push on it this way, in which case I can hold something up against the wall by pushing on it. But it's the friction between the wall and it that's holding it up, not necessarily the friction between it and my hand. So if I do that, I have to figure out the amount of the force that way. But if the force that's given is actually more at an angle, so again, we'll try to convert it into polar in order to be able to figure it out, then it's the portion of it that's this way that matters, which is this part. Which again, I have to ask, is it F, is it sine theta, is it cosine theta? If I push straight into the wall, that's theta 0, I should get the maximum. Therefore,
We're
cosine.
finding the
Yeah.
bottom. So it'd
Yeah,
be
so-
sine.
If I were to push straight into the wall,
Cosine.
theta would be 0. I should get the maximum result, which is cosine.
Cosine.
So it would be F cosine theta would be the contribution to the normal. And therefore the friction would be mu F cosine theta in that case. And then obviously you have mg down. It's driving it to accelerate, but when you go to put it together, you have to keep in mind that you have a force this way, which is F sine theta, which is lifting it as well.
Was there one in particular you wanted to inquire about? Linear speed, revolution, angular velocity, all sorts of speed to go over. I thought we were doing so well. We left here on Friday going like, yeah, we understand, and we did it, and kind of did. And then I couldn't remember the other chapters.
How did you do with working through the questions?
Pretty
We did
Were
good.
you
fairly
able
well
to
for
do-
chapter 6.
Like the old ones, because you
Yeah.
said it's like,
Yeah, so the ones where we just did little notes, you were
yeah,
able to finish
yeah,
them
we
for
finished
that.
them, we got them right. Yeah, so
And the other ones that where I went through the whole solutions, you're able to do them without any notes?
no, it was too long to review, to be honest. I double speed everything, and I'm like, wait, go back. Yeah. So we've both gone over
Well, not
seven
necessarily to
before.
watch the whole video, but for you to be able to sit and do the question.
Right, but then it's just,
I think that we're pretty good. Like, I can start it, and then I'm like, okay, I got it, but then I get stuck, and then I have to watch it, and
yeah, that's a good point. It's like, wait, we started, or that you're looking and you're like,
It might feel like memorization, but in getting to where you can do it independently, there's
Right.
Mhm.
still something there.
this was all,
I mean, that's how I got through a lot of classes. Classmates didn't understand, but I could do every homework question blind, even if I had to memorize it, because I didn't fully understand. And it would really frustrate me if there's a little part that I knew it was memorized that I didn't really understand.
yeah, because memorization is not, it's
I
really
try to
not,
make that the
obviously.
minimum, but you don't want any less than that. If you don't have that, then there's nothing you can throw down on the page.
This formula that you gave us, this is only valid in
That's-
this specific instance, correct?
That's,
The velocity
that's fall or
equals
rise. It's a vertical
fall or rise. I'm
So
writing
that would
this down.
go in the energy category, and it's just a solution to
To the velocity.
yeah. If I
Okay.
say that 1/2 mv squared equals mgh,
Oh, and then you're just moving the v.
I can solve it for v
Okay.
because the m's cancel, and it's square root of 2gh.
So you could just cancel out the masses if there's no mass. Is that what we've been doing? That's what our professor does as well, right?
Yeah.
Notice on. Okay.
Just assume the mass. Just say if it
It's
wasn't
one.
talked about, just use m.
Okay.
Not 1, just use m, and then hope it'll go away.
Oh yeah.
Okay.
In general, if you need a certain variable and you don't have it, that means it's going to have to cancel out somehow. So you just throw it in there.
Okay.
My last question is still change in momentum. How do I find change in momentum?
Where did it fit in? I guess it's right.
Because I'm
There's a
not
little space right about there.
It's like
Yeah, well, if
MVF
momentum
minus MV.
is MV, then change in momentum is change in MV, but the M doesn't generally change, so it's M change in V. The change in V is going to be V final minus V initial.
Come on. How shall we study Christmas? Oh, good lord. Okay.
Yeah, for me, going into the test is tomorrow or
No, it's Thursday.
Thursday. Oh,
Yeah. Yeah.
yeah. Headed into the test, I would firstly be able to do everything that's been assigned blind, even if that comes down to memorization.
Okay.
And then having achieved that, I would then get into the book and look for the most similar question you can find and attempt it.
Our book is so complicated because it's online. Have you looked at the book? Yeah. I was actually doing those review problems.
Typically, my books are all kind of ancient, but
I don't think physics changes
it
though.
does not change. But more books needed to be published because teachers needed to write books. What else are we going to do?
I even have like a physics for dummies book. But it's not called
One of
dummies.
those too. Oh, I put a book here, didn't I? Where's the good one? Oh, one of my students has a book.
What is the good one called? Maybe I'll go to the library.
It's green.
It's green. Okay.
It's the book that I studied when I was in college. Wait, well, anyway, not over there. The calculus book, it shows the same thing. It's got to be in there. Any given chapter. This is the real reason they rewrite books, or just to make them a little more useful. Like pick any given chapter.
Any given chapter.
There's always going to be at the end chapter review exercises. See here, there was the chapter exercises, right? That's the
Right.
exercise set. That's typically what's assigned. It's chapter review exercises, and then for a lot of chapters, we're going to have making connections. This is connecting this chapter to previous chapters. Yeah, that's really their chapter tests, but they're calling making connections. The review exercises then is closer to the test than
Okay.
the exercises. The exercises are meant to build you step by step. The review exercises are not given in that so obvious order. Because you're meant to have already learned it, and it's more testing you on what you can do.
Feels like nothing.
So,
Feels like nothing for now.
so you got 3 chapters.
Yeah.
Go to the end of them, find what they call review or chapter test or whatever.
Okay.
Pick out, a certain number. You think your test is going to have 7 questions, you said. So it's a matter of picking out maybe 14 questions out of there that you think are effectively the test for you. And then attempt them. And then ultimately, you get as far as you can, and then I can solve them for you if it doesn't work out in the end.
Okay.
I could always, if you make up a test like that and you send it to me, I could always just do this even if you can't be here.
Okay. Thank you. That would be great. Oh. Conceptuals. All right. We have our work cut out for us.
We should think about it a little every day.
It's funny because I did 7, the impulse momentum before I saw you, and then we went over it and it was great. And then I didn't do that and I did something else for like 2 days and I don't remember.
Every single day it trades. It's amazing, and the same thing happens to me.
Oh, that's a little harder to believe. How long have you been doing this?
Tutoring?
Yeah.